Good evening. Hope I'm audible.
Yes, yes.
Okay. So, is my screen visible?
Yes, madam.
Okay. So, today I'll be handling the session. You would have seen the third problem in problem sheet 2. It states that, let me just write it over here. The problem 3 states that the in order traversal of nodes in a binary search tree, that is BST, results in sorted order of the values in the nodes. This is the first subdivision related to the third problem in problem sheet 2. And there is also one more problem related to the complete binary tree. It states that the level order traversal of nodes in a complete binary tree, you can see that if you have ith node, the children of the ith node will be at position 2i and 2i plus 1. These are the two subdivisions in problem 3. I'm not going to teach you how this has to be done. You may have to use the principle of mathematical induction to solve this. So I'm going to give an overview of what mathematical induction is, and I'm going to explain that with respect to some examples. So moving on to what is mathematical induction. So what we have to do is we have to prove some statement. We can, when we want to prove some statement, we have to consider the parameter. For example, we all know the basic equation 1 plus 2 plus 3, etc. up to n. Can anyone tell me what does it sum up to? What is the sum of n natural numbers?
N into n minus 1 by 2.
N into n minus 1 by 2. Is he right?
n plus 1 by 2.
Yes.
N
N
plus
into
1 by
n
2.
plus 1 by
Plus
2.
1.
So this is the basic thing that everyone knows. We can prove this by mathematical induction. So what we do is, the step 1 is nothing but base case. So this we call it as problem that depends on n. P of n is nothing but the statement. The whole problem, the statement that we want to prove, we call it as P of n. Now what we do is base case is nothing but we consider for n is equal to 1, or you can consider n is equal to any fixed number. So when I consider n as 1, this statement becomes 1. N is equal to 1. So the left hand side, it's going to contain only 1. What about the right hand side? It is 1 into 2 by 2. You ultimately end up with 1. So this statement holds for n is equal to 1. So P of 1 is true. We are able to verify that when n is 1, this statement holds. This is nothing but the base case. Now we go for induction step. Induction hypothesis. Induction hypothesis. So what we do here is, for some natural number k belongs to n, I'm going to assume that P of k is true. The statement that we are going to prove is 1 plus 2 plus etc. up to n is equal to n into n plus 1 by 2 for all natural numbers. This statement is true in general. That is what we are going to prove. So we started with the base case, proved that P of 1 is true. Now induction hypothesis is our assumption. We are going to assume that P of K is true for some K belongs to N. When you assume this being the induction hypothesis, next step is nothing but induction step. Induction step is we are going to prove that P of the next natural number K plus 1. P of K plus 1 is true. You have to prove this. So how do we prove it? We are going to prove this with the assumption that P of K is true. So this is going to help us in proving P of K plus 1 is true. So what we are going to do is, we will write the statement P of K plus 1, which is 1 plus 2 plus 3 plus etc. plus K plus the last number is nothing but K plus 1. This being the last number that we consider. This is nothing but P of K plus 1. This we have to prove that here in place of n you have K plus 1. So our expression will change to K plus 1 into K plus 1 plus 1, which is K plus 2 divided by 2. You have to prove this. How do we prove this? So what we do is, we have to consider this. We know that this part is nothing but P of K. What is P of K? We had assumed P of K to be true. 1 plus 2 plus etc. up to K is equal to K into K plus 1 by 2. So this turns out to be K into K plus 1 by 2 plus this natural number. This is nothing but LHS. We consider the LHS, we're going to prove that that's equal to this expression. So K plus 1 being common in both the terms, I take it out. So what is remaining? You have K by 2 plus 1, which is nothing but K plus 1 into K plus 2 divided by 2. So we have got this expression. So the base case, you have to prove that it is true for some any base value, k equal to n is equal to 1 or 2 or 3, any fixed value you can prove. And induction hypothesis, you assume that the expression, the statement is true for some k, which is a natural number. Now, induction step involves proving that P of K plus 1 is true, assume with the assumption of induction hypothesis. So using the previous step, the hypothesis, you're going to prove the P of K plus 1 is true. Hope I'm clear. If not, please let me know. I can explain this once again. Do you have any doubts?
It's clear.
Okay. So in the same way, you can consider one more example. You can take, you can try this later. 1 plus 3 plus 5, just to practice the mathematical induction. 2n minus 1 is nothing but n square. You can try this out later. Using the same methodology, you can try this. So this talks about mathematical induction. And there is one more term called as strong induction. So what's the difference between the previous methodology and the strong induction? Here you see that you have the base case to be the same. P of 1 is true, or any particular value P of A is true. You can prove that. So hypothesis, the induction hypothesis is nothing but, this is the place where you see the difference between the strong induction and the normal induction that we have learned recently. So induction hypothesis says that P of 1 has been already proved to be true. We also assume P of 2 to be true. So P of 3 is true, etc. P of K is true. We assume this. Assume that P of 1, P of 2, etc., P of k is true for all k between 1 and strictly less than k. So for all these values, we assume that it's true. Now, induction step says that you have to prove P of k plus 1 is true. This is to be proved. So the base case is P of 1 is true. Induction hypothesis, you assume all these to be true. But in case of the previous methodology, you only assume P of k to be true for some k which lies between 1 and k, 1 and n. And we prove that P of k plus 1 is true. Strong, we assume more strong conditions in this. That is why we call it a strong induction. And let me just give an example to illustrate a strong induction. You would have learned about a recurrence relation. So let me just give an example with respect to recurrence relation. So problem is if f of n is equal to twice of f of n minus 1 for n greater than 1 and f of 1 is equal to 1. Then you have to prove that f of n is equal. Does anyone know the answer for this? What is f of n? Then f of n is nothing but 2 bar n. So previously, just the mathematical statement we proved using induction. Now we are going to use the strong induction to prove this recurrence relation. What we do is we start with the base case. So base case, we always start with n is equal to 1. N is equal to 1. We know that it's 1. And does it satisfy this condition? F of 1. This is what we are supposed to prove. So f of 1 is nothing but here f of 1 is nothing but 2 times f of we consider n strictly greater than 1. So we don't start with 1, we start with 2 here. F of 2 is nothing but when you substitute 2 here, twice of f of 2 minus 1, which is f of 1. So this is going to be 2. F of 1, we already assumed it to be 1. So f of 2 is nothing but 2, which satisfies this condition. So base case is done. Now induction hypothesis says that we assume f of 2, f of 3, etc., f of k to be true. This is our assumption, assume, where k is lying between 1 and n. So this is our induction hypothesis. Now we are going to prove the induction step for k plus 1. So to prove, yes, please.
In base case, f of 2 should be equal to 2 power 2, right?
No, see, I'm sorry. Yeah, you're right. 1 minute. This is f of 2 is, I think there is some issue with this 2 power n minus 1, I believe. Yes, I'm sorry. This is 2 power n minus 1. This is wrongly. I'm sorry. Thanks for identifying the issue. It's 2 power n minus 1. So you have f of 2 as 2, hence the statement holds. Now we assume the induction hypothesis as f of 2, f of 3, etc., f of k to be true for k lying between 1 to n. Now to prove f of k plus 1. What do we have to prove f of k plus 1 as? 2 power k. So this is what we are supposed to prove. Now what we do is we consider f of k plus 1 using the recurrence relation which we had earlier. It's Nothing but f of n is twice of f of n minus 1. So this is going to be twice of f of k. And now this is going to be continued. You know that this is again equal to twice of 2 times f of k minus 1. And why do we say that we use strong induction here? We know that for induction, normal induction, f of k plus 1 is nothing but 2 times f of k. But for f of k to be true, f of k minus 1 should be true. So all these are involved. That is why we have strong induction. All these assumptions are required. Till f of 2, we have to assume things. That is the reason we use strong induction. If you are going to use only f of k to prove f of k plus 1 is true, it's nothing but normal induction. When we use all these in our proof to prove that f of k plus 1 is true, using f of 2, f of 3, f of k, we say that it's strong induction. So this now becomes 2 square f of k minus 1. Now this can be written as 2 cube f of k minus 2. So this can be generalized, and at one point you get it as 2 power k into f of 1, which is nothing but f of 1 is 1, so you get it to be 2 power k. So this is what we are supposed to prove. We have done it. Hope the procedure is clear. Can you identify the difference between normal induction and strong induction? If at some point, if you have difficulties to understand, please let me know. I can explain this again. The base case, we start with n equal to 2. We were able to prove that f of 2 is nothing but 2 power 1 minus 1, which is 2.
Ma'am,
So, yes.
here, in case if we use weak induction,
Yes.
then also like if we in induction hypothesis we will be assuming like till like f of k is equal to 2 power k, right? Sorry, 2 power k minus 1.
Yes, f of k is
So
nothing but 2 power k minus 1. You're
so
right.
if it is like in k plus 1 step, in the first step if we substitute the induction hypothesis by weak induction, we can also prove the same thing.
No, see, you will be expressing f of k plus 1 as twice of f of k.
Yes,
How
ma'am.
do you know that f of k is nothing but twice of f of k minus 1?
No, in f of k we can substitute, it is instead of substituting from the question, we can substitute from induction hypothesis, weak induction hypothesis, that it is already proved to be 2 power k, right?
Yes, it is already proved to be 2 power k, but you know that f of k minus 1, see, f of k is nothing but twice of f of k minus 1. That's true. But what is f of k by the result of the given statement? It is 2 power k minus 1, right? How can you use that without knowing whether it satisfies or not?
That is what we prove in the we suppose in the induction hypothesis.
Exactly. For f of k, we know this. But subsequent steps for f of k minus 1, when you want to extend for f of k minus 2 and all that, we need
Yes,
the
this
result.
I understood, because we are substituting it from the question and we are
Yes.
doing it repeatedly. In case
Yes.
if you we don't substitute it from the question and we assume the proof, I'm giving a different proof.
Yes,
If
please.
we do it with a weak induction is also a possible methodology for this question, right?
Can you tell me the proof? How do you go about?
Base case will
You,
be the same. F of
yes,
2 will be
you're
f2
right.
into f of 1.
Mm.
And then induction hypothesis will be assume f of k is equal to 2 power k.
Yes.
So to prove
And k, assume for some k.
for some k.
Uh-huh.
So we have to prove for k plus first step.
Yes.
So f of k plus 1 will be equal to 2
Mm.
times f of k.
Yes.
And by the induction hypothesis, f of k is 2 power k minus 1. And so
Yes, you're right. You're right. You're right. That is another way of proving. You're right. Exactly. That is by using the weak induction. But to illustrate the strong induction, I'm using this kind of example to prove this. You're right. Directly for this, 2 power k holds, so 2 power k plus 1. Certain statements, either in mathematics or in other in computer science, we have to go about only strong induction. Weak induction may not apply. There are problems like that. Here, both are applicable. You're right.
thank you.
So, does anyone else have doubt in this? So let me go with the problem on graph theory. Is everyone have idea about trees in graphs? The concept of trees.
Yes.
Yes. So what is a tree? What is a tree?
Connected acyclic graph.
Very good. It's a connected acyclic graph. So we have seen more on trees, BST, complete binary trees. So many concepts have been taught to us. Now we move on to the trees in graph theory. You know that um, how many leaf nodes can be possible in a tree? Can anyone tell me the answer for this? Given a tree, how many leaf nodes are possible? There is a theorem on the number of leaf nodes in a tree. Does anyone have doubt answer for this? Any tree?
One.
N minus 1.
Depends on the height. 2 raised to power h.
H. So if the height is h, you say that the number of leaf nodes are h. 2 power h.
2 power h plus 1.
Okay. So any tree has at least 2 leaves. Do you know the statement? At least 2 leaves. There must be at least 2 leaves for any tree. So this is one important property that I'm going to use. And the problem that I'm going to prove is, to illustrate the mathematical induction, I'm going to take a problem on tree and prove this statement. A tree on n nodes contains n minus 1 edges. Have you learned this? Any tree on n nodes, n vertices will contain n minus 1 edges. Very familiar statement, right? In graph theory.
Yes.
So this, I'm going to use the induction property to prove this. So what I'm going to do is, you can either prove this with the help of the induction on number of edges or the number of vertices. These are two parameters of the graph. So either with the help of edges or with the help of vertices, you can prove. I'm going to prove this with the help of induction on vertices. I'm going to prove the induction using induction on vertices. So what I'm going to do is, the base case number of vertices. So number of vertices, we call it as n. So the base case, when n is equal to 1, what is the tree with exactly one vertex? A singleton. You have an empty graph on single vertex, right?
Yes.
How many edges are possible in this tree? There are no edges, right? Singleton
Zero.
vertex. There is
0.
a null
Zero.
graph. Zero.
Zero.
So
Zero.
it can be verified easily. Tree on one node contains 0 edges. So the base case is obviously true. Now moving on to the induction hypothesis. So what do we do here? Can anyone tell me what the induction hypothesis is? What are we going to assume?
For k vertices, k minus 1 edges.
For k vertices, yes. For a tree on k vertices, for a tree on k
Okay, what
vertices,
time?
there are
K minus 1 edge.
edges. Yes. So now we are going to prove, and what is k here? I'm going to assume this as for all k lying between 1 and n. This statement is true for all k lying between 1 and n. Induction step is going to be, I have to prove for how many vertices? K plus 1 vertices. So let me consider a tree on k plus 1 vertices. I should prove that this tree has how many edges?
K.
K edges. To prove T has K edges. So how do we go about? Does anyone have a clue on this? Even if it's wrong, no issues. Please think and let me know. How do we go about? Our ultimate aim is to use the induction hypothesis. We have a graph on k plus 1 vertices. How do you use the previous step?
We add one vertex and one edge because for
Okay,
adding one vertex we need one more edge.
okay. How do you say that only one edge only will be added? It can have two more edges as well.
Uh,
And you say that this statement is true and you are constructing a new graph, but I have a graph now which is totally different from the graphs that I have considered in induction hypothesis. I'm given a tree on k plus 1 vertices. How do I prove that it has k edges? And a clue that I can give you is the one I said before, any tree has at least two leaves. You can think over about the statement and get me proof idea for proving the induction step.
Keep adding the tree with the one nodes.
Keep adding the tree with one more edge, or can you repeat? I didn't get you.
Means tree with only one node, then one more node is added. So one edge
Okay,
also added in the tree.
okay.
So I think that way
So
we can.
in that case, you are connecting a vertex with another vertex. An edge is added, right? For a tree on
Yes,
one vertex.
yes,
Then you
yes.
get a, when you repeat this procedure, you get a path. But we are talking a general case, tree. Tree need not be only a path. It can be anything. Do you agree that the tree T has at least one leaf? We have seen that it has at least two leaves, right? What is the degree of the leaf vertex?
One.
What is the degree of one?
0, 0,
Zero.
It is
Leaf,
one.
it is one.
1,
one.
1.
For a leaf, the degree is always 1. So what we do is, the whole graph consists of k plus 1 vertices. So I consider a leaf, okay, graph T, and let me assume the vertex V to be the leaf vertex. Okay, so let me consider this edge to be E. So this is nothing but T minus the edge E. Or I can remove the vertex V as well. If I remove the vertex V, it is going to be T minus V. Can you visualize this? I consider, anyway the tree will contain at least two leaf vertices. I pick one leaf vertex, so which is nothing but V, and I delete this vertex V and the edge E. If I delete the vertex V, definitely the edge will be removed. So this is the graph. The circle is nothing but the graph T minus V. Can you tell me whether the graph T minus V is connected or not?
Repeat it again, ma'am.
I'll repeat it. See, we consider a tree on k plus 1 vertices, right? Any tree will contain at least 2 leaf vertices, 2 vertices of degree 1, definitely. So pick one leaf vertex, let it be V. So what I do is definitely there will be only one edge adjacent to V. So delete the edge or delete the vertex V from the whole graph T. So we have this graph without this edge and the vertex. T minus V is this. It doesn't have the edge E. How many vertices will T minus V contain? Can anyone tell me? How many vertices will T minus V contain? Initially, it contained K plus 1 vertices. We have deleted one vertex. So how many vertices will it contain?
K minus 1.
K.
K vertices. Initially, we had K plus 1 vertices. Now we deleted one vertex from the tree. So when we delete one vertex, it's now going to contain K vertices. Got it? Right? And the previous step, induction hypothesis, we assumed that any tree on K vertices contain K minus 1 edges. So this is going to contain K minus 1 edges. Can you tell me what should be the next step?
K minus 2.
K minus 2. No. See, you have the tree by removing the vertex V, you got T minus V. One vertex removed. So the number of vertices in T minus V is K vertices. Now, by the induction hypothesis, this will have K minus 1 edges. Now, how do I prove that the graph T, the tree T, will have
Now,
K
ma'am, again
edges?
we remove the one vertices and we reach to the lastly one vertex.
No. T minus V has K minus 1 edges is now known to us because of the induction hypothesis. Now, what was removed? This edge was removed. Now, if I add this edge, how many edges will be possible in T?
Then K minus 2.
You're adding one more edge. Please understand carefully. I'll repeat it. See, maybe I can do it with an example. Take a arbitrary T. I have a tree over here. So let me call V1, V2, V3, V4, V5, V6, V7, V8, and V9. These are the vertices in the tree T. Now what I'm going to do is how many vertices does it contain? 9 vertices. And I know that for 8 vertices the statement is true. So what I do is, can you tell me the leaf vertices? How many leaf vertices are there in this graph?
5. 6.
5. 5.
1, 2, 3, 4, 5, 6. 6 leaf vertices are there. I choose arbitrarily one of the leaf vertex. So what I do is I pick V5 to be my leaf vertex. V5 to be my leaf vertex. I can take any of the leaf vertex for that matter. Now what is the graph that is remaining after removing V5? It is V1, V2, V6.
-1, madam.
Sir? Yes, one minus of this. This edge has been removed. Okay.
-1.
So
Okay.
V3, V7, V8, V4, and V9. Now, initially we had 9 vertices. Now, after removing V5, T minus V5, it has 8 vertices. By induction hypothesis, this should have 7 edges. And when you add this edge, you get 8 edges. Am I clear? The induction hypothesis is true for any number of nodes with one less than the original graph. So the induction hypothesis is true. Since it has 8 vertices, it should have 7 edges. 7 edges. And when we remove one edge, now when we add that edge, you get 8 edges in total for the whole tree. Hope the procedure is clear. Please let me know if this is not clear. I can explain it once again.
It's clear, man.
Clear? Okay. So this is how we use the principle of induction to prove some statement. When you have a problem on graph theory, you can either go with the parameter as n, the number of vertices or number of edges. You can try the same problem using induction on the number of edges. That is also possible. You will have to discuss various cases for that. So you can try that. And the original problem that we had in the problem sheet, this was the statement. So you will have to choose a parameter. Can you think of what parameter do you choose in this? In the problem of trees, I told you we can choose either the number of vertices or the number of edges can be the parameter. Here, what is a parameter that you choose? Induction on what do we do? So think about it. If you have any further questions, you can ask me. So obviously you have to go with induction for the problem 3. So I've given a basic idea of how to apply induction, the base case, induction hypothesis, and induction step. So base case, you have to prove. Induction hypothesis, you have to assume. And induction step, using the assumption, you have to prove the next value, k plus 1, to be true. And one more thing I would like to tell you is that in the dashboard of this course, you can see a file, instruction file. You have the instructions, important instructions in the file, and you also will see the textbooks, references for this course. The links, resources, online resources are also given in that, and our email IDs are also provided. So you can text us if you have any issues in the understanding any concept. Any other doubts? Yes.
Ma'am, last graph question.
Yeah.
If we do the induction with edges,
Which
then-
problem? The third one.
no, ma'am, in the mathematical induction explanation, the last graph theory
Okay.
question,
Okay. Okay. Yeah. Tell me.
if we if we use a parameter as edges,
Yes.
if we remove an arbitrary edge,
Mm.
then we should use only strong induction. Is there a process for doing weak induction, or like there was a result here used, right? 2 leaves are there, so we can use weak induction, and we
Yes.
use that 1 leaf will be there, we can remove it.
Yes.
In case if we for edges similarly, do we need? I understand that if we remove an edge, trees will be of smaller vertices, and we
Yes.
can use strong induction to prove it.
Yes.
But
There is a possibility of using weak induction as well.
is there a possibility of using?
Yes. Yes, that's there. Your choice is important. You can think over it. The idea that you will have to choose the longest path, in which case you will be able to prove it using weak induction as well.
Okay.
Okay, think about it. Once you remove an edge, the remaining graph may be connected or disconnected.
Yes.
So
Yes.
think about it. You can try doing it actually. Once you get the idea of what strong induction is and what weak induction is a normal induction procedure I described earlier. So depending on the problem, you can apply whichever suits that.
Thank you.
Welcome. Are there any more questions? And
Hello, madam. Hello, madam.
yes, sir. Yes.
I have some basic question.
Yes, sir. Please.
What are the prerequisites to understand this complete data structures and algorithms now? What sir teaches?
Prerequisite. If you just prerequisite in the sense, what do you mean by that? Any other course you should have done to understand this course?
Yeah,
Is
yes,
that
yes,
you
yes,
mean?
yes. Yes, yes. You said talking about the graph theory and all. Like,
Graph theory is just a part of it, actually,
okay.
which will be dealt in future. Like when sir starts algorithm, he will give the idea. But graph theory, I have not done much in graph theory right now. Graph contains set of vertices and set of edges.
Yeah, that is okay.
I was dealing with only the basics. Tree you would
Yeah,
have learned, right? Binary tree and all that you would have learned. So
yeah,
I started with the basic structure. That's all. I didn't do much on graph theory right now.
okay.
With the node
Any
concept, I've just explained.
yeah,
Yes.
any mathematics is required, like mathematical background.
No, sir. Nothing is required. You can very well understand this procedure.
Yes, okay. Thank you.
Welcome, sir. So if there are no questions, we'll wind up this session. In case you have any doubts, please mail us. The mail IDs are provided. Sir's mail ID is also provided, and my mail ID is provided. And regarding other things, queries like getting the assignment questions and all that, you have to contact the NPTEL team. So, related to the problem sheet or to the concept, if you have doubt, please contact us. Thank you.